this. Okay, yeah, the LP norm, everybody knows it here, I guess, and we will just depict the Lebesgue scale here. No, this is L infinity, this is L1. Here we depict 1 over P. This is L4, L2, and so on. So here is 1 over P, what is in this real line. Now in the vertical direction, we will put smoothness. We measure smoothness essentially with differentiability classes, C1, C2, C3, and the norm that is associated to this space is just adding the last available derivative. No, for instance, C3. C3 is the L infinity norm of the third derivative with all the infinity norms of the previous derivatives. Okay, up to the original function. Okay, then we can go combine both things and get the Sobolev scale. This measure both at the same time integrability and smoothness. And this is just taking, for instance, Sobolev SP. Sobolev 3,4 is taking the third derivative, its LP norm, and then adding all the previous derivatives in their norm in LP. Okay. Now we can go between. There are between C1 and C2. There is C175, for instance. So we have these Herglotz continuous spaces that fill the gaps between the differentiability classes. Okay, and it's measured like this. So we take the last available derivative. Okay, this is the integer part of S of the smoothness. So for instance, in C175, this would be 1. We take the first derivative of F, and we take the difference between 2 points and divide by the difference between 2 points raised to power S. And this is the fractional part. Okay, 0.075 would be here. Okay, this is the Herglotz scale. Okay, this can be also done between Sobolev spaces. We can interpolate them, and we can find these fractional smoothness spaces. Here is Sobolev 3, smoothness 1, and you can find this smoothness 3/2. And this can be done using interpolation or some other tools. Okay, and we will be talking about these Bessel potential spaces indicate with Sobolev with this W. We use W because Bessel potential and Sobolev coincide in the natural indices of smoothness. Okay, there's also this Bezoff scale, Triebel-Lizorkin scale. Okay, well, there are several ways to fill the gaps. Okay, come on, let's move on. By the way, there is this important idea about critical, supercritical, subcritical. What is this? Okay, we have these Sobolev embeddings that allow us to say that if a function is in a certain Sobolev space, then automatically, following this line, you are embedded in all the spaces that are below, okay, with less smoothness. Following this line. What is this line? This is the line of spaces with the same homogeneity in the seminorm, okay? For instance, here is homogeneity 0. This is L infinity or continuous functions, whatever is here, and all the spaces in this line, the line given by this equation, S times P equal D, have the same homogeneity. This is called the critical line. All these function spaces, for instance, are functions that are also in VMO, okay? And here you get, the Sobolev embedding gives you Herglotz continuity, and below you just get some extra integrability. If a function is in Sobolev SP, you get that the original function has some bigger integrability than the original, okay? Okay, I hope that this scheme is more or less clear. We will be coming back to it during the talk. Let me just move forward. Okay, I want to stress during this first section about properties of composition for bi-Lipschitz Sobolev functions. It goes as follows. We take a smoothness greater than 1 plus d over p. So this is not the critical line, but just adding 1 to this critical line. So go here, it would be this line here, the parallel line above. We are talking about this region here. Okay. These function spaces we take a bounded Lipschitz domains, omega j, omega 1, and omega 2, and two functions fj, f1 and f2, that are f1 maps omega 1 to omega 2, okay, and it's Sobolev mapping. Okay, both of them are Sobolev with smoothness S and integrability P. Okay, now if they are if f1 is bi-Lipschitz, then the composition is also in the same Sobolev class. Okay. Moreover, if F1 goes to is a homeomorphism, then the inverse is also in the Sobolev space. Okay. This is a result that we were not able to find it in the literature, so we just did it. The proof is quite easy. I will explain you how does it work, and if somebody already knew it, please tell me, because maybe somebody did that before. But I will tell you how does this work. It's quite it's very simple notion. Okay, this result works more in general. Sorry, let me see. Okay, this result works more in general for also below this critical line. Okay, this line. For smoothness above 1, as long as we force the derivative to be an infinity. Okay, so we ask that the function is Lipschitz at the same time. If it's Sobolev and Lipschitz, then automatically the same results will apply. Okay. Okay, and also for the Triebel-Lizorkin scale, the same results will work, as long as we are not in the natural indices. In the natural indices, we don't have a proof. Okay, for dimension or for dimension 1. For dimension 1, the proof is already done by these authors, Bourdeau, Musset, and Sickle. And for the composition and for the inverse function, it's in dimension 1. It's done in and my work with Astala and Sackman. Okay. Okay, so let's try to. I will give you a hint of this proof, of the proof of this fact. Okay, the composition of two Sobolev functions is Sobolev. Okay, as long as they are F1 is bi-Lipschitz. Okay. Now, the first idea that we need to use is this interpolation. Interpolation for Lipschitz functions. Sorry, for Lipschitz functions. So we assume that the function is Sobolev and Lipschitz, and then automatically it's in all the spaces in between. Okay, and here how we write it? We say that the gradient of the jth gradient of the function, that means the jth derivative of the function, has some extra integrability. It's this integrability here. Okay, this may be a mess, but for me it's much more clear with the graph. This is what I am saying. If a function is Sobolev 5p and at the same time is C01, so it's Lipschitz, then automatically it's in all the spaces in between. Okay, and in particular, if we divide, you make just the Thales theorem, you will find exactly what are the indices that you need to put. What is this relation? Okay, this is just using the Thales theorem here. Okay, you divide in 4 parts, then you find these exponents here. That this is this coefficient here that gives you this extra integrability for each gradient. Okay, the first gradient will have a lot of integrability. The second gradient a little bit less. The third gradient will have just a little bit more, and the fourth gradient is just p integrable here. Okay. Okay, fine. Let's move forward. This is essentially by a result by Runst and Sickle. They work in L infinity, not for Lipschitz, but for L infinity functions. But okay, raising these to Lipschitz functions is just a matter of, is a technical proof, very quite easy. No, there is no deepness here. So let's move forward. Okay, so second tool that I need to explain you this composition rule is the chain rule, or Faà di Bruno's formula, if you want. So what is the chain rule? Okay, the derivative of G composed with F is the derivative of G at F times the derivative of F. If you take a second of this, then if you differentiate the first one, you get a second derivative, an extra term here. And if you differentiate the second term, you just take a second derivative here. Okay, now we differentiate again. If we differentiate the first guy is this one, and you have 3 terms. If you differentiate one of these guys here, you get this one. If we go here, you also get this one. No, and you go this one. Okay, so you get this differentiation. I guess this is easy enough. Note what is happening here. Okay, if you compute the third derivative you have 3 terms. Second derivative, you have 2 terms. First derivative, you have 1 term. Because when, each time that you differentiate g, you get an extra function, an extra derivative for f. But the number of derivatives here is 1, 1, and 1. So you have 3 derivatives here. Here you have 1 and 2, 3 derivatives here, and here you have 3 derivatives. So the generalization is the following. If you take s derivatives, s is a natural number here, then you have some coefficients. I don't care about this. And what will you have? You have some derivatives on the original function. Sorry, in the change of variable function f, and this number of derivatives needs to coincide with s. Okay. And how many terms do you have here? You have I terms, and these I terms is the same as the number of derivatives that you have taken, the same as we were saying before. Good. So this would be like this kind of Faà di Bruno's formula, or a version of it. And okay, but our function f will map Rd to Rd. What happens if we go from Rd to Rd? Well, then the derivatives will be a vector. You don't have one index, but a vector valued index of derivatives. This means that you differentiate for k1 times in the first component, k2 times in the second component, and so on. Then what will happen? Well, instead of having I derivative, you will have this vector I derivative. The number of derivatives will still be controlled by s as before, so this is the same idea. And just the number of alphas is also again the number of derivatives of the function f also will add up to s. Okay. Good. Note that each term will have at least one derivative. So this alpha is never all zeros. It cannot be all zeros. You always have at least one derivative. Okay. Of course, I guess you can feel why is this happening. Anyway, we have this formula, and now with these ideas in mind, we will try to see why the composition is also Sobolev. So this is the idea. What we have here now is we take absolute values, so we forget about these indices with these coefficients, everything. We just care about the number of derivatives. So we have here I derivatives for the second function f2, and just alpha derivatives for the first function f1. And now we want to see that this is an LP. This will be like this derivative of order s of f2 composed with f1. Okay, this is what we have here. We need to see that this is in LP. Okay, let's see that this is true. Then we will apply, of course, the triangle inequality and Helder inequality. Very easy. And what we get, we need to put here a p0 for this function and p sub l for each one of these L terms here. And these exponents satisfy that they add up to p, so that the Helder inequality works. Okay. And which exponents we will choose? We choose this the following. This is p0, is p times s minus 1 divided by I minus 1, and pl will be this thing here. Essentially is the same. And now we use the formula that I told you before. This is the interpolation I told you about 2 slides ago. And now we apply this. Okay, see. If you apply the interpolation here, this formula, you get these 2 elements. Okay? Okay. So this one is this one, and this guy here is this guy here. Okay. This is straight ahead. And about the other elements here. So what we have here, we have alpha L. Note that we have I terms and they are multiplying, so the exponents will be adding. This is the norm of f raised to power alpha L minus 1 divided by s minus 1, and you are multiplying them. Okay, but multiplying them is the same as summing in the exponents. But summing alpha, come on. Summing alpha L is s, and summing 1 I times is I. And the same will happen for the other guy. So the other guy is this one here is s minus alpha L divided by s minus 1, and you sum them. And if you sum s I times is IS, and if you sum alpha I times is alpha, sorry, all the alphas add up to S. For this reason, you get exactly the same exponent here as here. So you can group these elements. And you can group these two elements also, just paying the price that there is an extra S here, if you see. Okay? But the exponent here, S minus I, divided by S minus 1, and the other exponent, I minus 1, S minus 1, this equals 1. So here you can apply Young's inequality for multiplications, and what you get is this final result. Okay, so that's all. It's just Helder inequality, Young's inequality, and just thinking a bit. Okay, now let me move forward. I promise that I will get complex very soon. Now I'm quite real valued, but I will get complex soon enough. Now, what happens in the Triebel-Lizorkin scale? Okay, what is the Triebel-Lizorkin scale first? I didn't define you that. Normally, Triebel-Lizorkin scale is defined in terms of going to the Fourier side, taking these Littlewood-Paley terms, and then back and summing in a certain way. But this, in our case, is equivalent to the following definition, which maybe is more clear. We define, we take a function f. We take this part, this is Sobolev. So now we will take, let me see, smoothness S equal k plus sigma. Sigma is fractional, and k is the natural number part. No, the integer part is k. Okay, it's a natural number. Okay, so and now we have a certain restriction, but we will drop this later. We have this restriction. The fractional part needs to satisfy this, in order that everything makes sense. Okay. Okay, good. Then you take this the Sobolev norm for this integer part, for instance, and now the semi-norm, that is the really interesting part, is this one. What is this? This is like, remember, in the Helder scale. In the Helder scale, what did we have? In the Helder scale, you have this thing. Okay. Now you raise this to power q. Okay, you raise this to power q, and you take integral, and you need to make that all the scales have the same importance in this way, dividing by x minus y power d. Okay, and then you take also the LP norm in the x variable, and this is what is the semi-norm for the Triebel-Lizorkin scale. So it, as you see, in this way, it's quite clear that Triebel-Lizorkin is essentially, Triebel-Lizorkin is to Sobolev exactly what Helder is to differentiability classes. Okay, I think the slide is lost, maybe. The slide is lost. Let me try to connect that again. What happened here? Sorry, the technical issue. Okay, now it's coming back. I should share again the screen, I guess. Okay, it's back. Everybody can see that again?
Ahora.
Okay.
It's not coming? It's coming now. Okay. Cool. I cannot see it yet, but I guess that if you are fine, I am fine. Okay. So, okay, that's what I was saying. But there is this restriction. There is this restriction here for this norm. And this is because BAM functions will not satisfy that this semi-norm is finite if sigma is not greater than this. So we need to be in the most possible generality. We have to take a variant of this norm, that is taking integrals, means on balls. Okay, means on balls for this thing here. And this is what we have. This is I showed in the preprint that this norm for domains omega, I think for uniform domains, it's equivalent to the Triebel-Lizorkin norm again. And the difference here is that we take means in balls. Note that here you have this guy that is essentially taking the mean. It's like taking the mean here. Okay, this is the role of this guy here. This sigma is playing the same role as before, the Helder height. This is the scale invariant coefficient, the Haar measure, and okay, so it's essentially the same, but now it's you take means on balls. Okay. I just mentioned this. I will not use this during the talk, but the important idea that I want you to take is that what we are using is first order differences. And first idea. Second idea, it's only working for sigma between 0 and 1. So it's only working for smoothness that is not integer, our reasonings. Okay? Now, what is the idea? Now what we want to see is that f composed with f2 composed with f1, I don't remember the order, is fsq, no? We want to see that this is here, that this norm is finite. And this is the same as taking the last derivative, gradient k. I want to see that the gradient k of the function satisfies that norm is finite. Okay? And now the thing is that we have a difference. So what we need to do is to subtract the value of the function in two different points, and now we need to, of course, use again the Faà di Bruno's formula, but then you will have something that is evaluated at x, something that is evaluated at y, and there is a product of a lot of things. So you will what we do is just a telescopic summation to get this kind of expression. And still, once you are here, you are not safe, because if you pay attention, this is fine, and this is also fine, but note that here there is a variable y, and this is a variable y, and there is a variable x. So how can we perform here a Helder inequality? We need to have either differences or things evaluated at x. Things evaluated at y are not nice for us. So okay, the technical details are in the paper. You can check them. But essentially, the idea is you do again a telescopic summation here, and what you will have is some product where several terms may have a difference. You may have several terms that contain a difference. Okay, but then you will have to play around subtly, but with the same ideas, exactly the same ideas as before. You can prove also that this composition satisfies that the Triebel-Lizorkin norm is preserved somehow. Okay, that was it for real analysis. Let's go for complex. Sorry for that, but I think I needed to give you this introduction so that we can proceed. Now we will talk about the Riemann mapping in the Sobolev scale. So let's see. What are the implications of the geometry of a domain in the regularity of the Riemann mapping? Of course, if a domain has no tangents, as this von Koch snowflake, then the function itself cannot be C1, because otherwise you would have a tangent if the derivative could be extended up to the boundary. So Kellogg and Batchevsky showed in early 20th century that if omega is simply connected and Cn plus alpha, so a quite regular domain, n greater or equal than 1, and alpha strictly greater than 0, between 0 and 1, then the Riemann mapping inherits the regularity of the domain. So if the domain is regular, then phi is also regular as well. And what we wonder in this work is what happens with the Sobolev scale. Can we grant that somehow? Can we characterize when the Riemann mapping is in the Sobolev scale? And here is the theorem. This is in the joint work with Kari and Eero. Let's take a smoothness greater than 0, p between 1 and infinity, and in the supercritical part. Now suppose that omega is a bounded simply connected domain with Riemann mapping phi, and then we have the following equivalence. Omega is a Bezoff domain I will talk you about later what is exactly this definition, but essentially you can feel what does this mean. This means that the parameterization of the boundary is in the Bezoff scale, is in the Bezoff space. Okay, that the domain, as I was saying, is Bezoff domain if and only if the Riemann mapping is Sobolev, S+1. Okay, and the inverse is also Sobolev. Okay, quite fine. And this is equivalent to another different thing, but quite similar. It's just replacing this condition on phi minus 1, but just being an infinity, its derivative. So being bit by Lipschitz. We only need that phi is by Lipschitz. Okay, this is and this is what we really will show during this talk. Okay. Okay. Let me move forward. Okay, first idea, the Herglotz formula. Consider the following. This is an idea by Pomerenke, as far as I know. At least it is in the book of Pomerenke. Take capital phi of z as the logarithm of 3 prime. The logarithm of 3 prime. This is well defined because d is simply connected, and 3 prime, since it is bi-Lipschitz, then this is far from 0, so this is well defined, and it works well. In particular, we define gamma to be the boundary values of the imaginary part. Okay, of the imaginary part. That is the argument of phi prime. The imaginary part of the logarithm is the argument. You well know that. Okay, this is a well-defined continuous function in our setting. Now recall the Poisson kernel in the disk. The Poisson kernel in the disk that solves the Dirichlet boundary value problem is this this thing here, which is the real part of this zeta plus z divided by zeta minus z. And this is nice because this kernel is holomorphic, so out of its poles. So what we get is that the Poisson extension of gamma is not only harmonic, it's holomorphic, and moreover it's real. So the real part of that is the imaginary part of this, is exactly the imaginary part of this guy because is the extension of its boundary values. So the difference between these two guys needs to be just a constant. Okay, and this constant needs to be exactly the value of the real part at 0. Okay, you can just think about it for a while, and you will. This is an exercise for you. Okay, and in particular, this is exactly this logarithm. This is not important for us. What is important for us is this part here. So the idea is we can recover phi out of gamma using the Herglotz extension. This is the lesson here. Okay, and Poisson extension maps Bezoff functions to Sobolev functions. Okay, in particular, Bezoff is what is called the trace space of Sobolev. This means that every Sobolev function, if you take its boundary values, can be represented as a Bezoff function, and vice versa. If you have a Bezoff function, you take just the Poisson extension and you find the Sobolev function, whose boundary values are the initial function. So Bezoff is, and this is why it's so natural that in all our results, these will be appearing every time. This loss of smoothness is the natural loss because it's the relation between the functions and the boundary values. Okay, Sobolev functions and its boundary values. Okay. Idea of the proof. Let's assume that omega is a Bezoff domain. And what we will prove is that gamma is in Bezoff. This here is s plus 1 minus 1 over p. Here the smoothness will be just s minus 1 over p. Okay, and the less of smoothness. Let's assume that this holds, and let's see that this is enough for our purposes. Let's see that this shows that phi belongs to Sobolev SP is what s plus 1. Sorry, s plus 1p. This is what we want to see in the unit disk. Okay, let's show that. The Hilbert transform is bounded. So note that what is the real part of the logarithm of phi prime? The real part is the imaginary part. no, the Hilbert transform, the real part, sorry, is the Hilbert transform of the imaginary part, and the imaginary part is gamma. Okay, so since the Hilbert transform is bounded in the Bezoff space, this means that the real part is also in the Bezoff space. So the imaginary part and the real part are both in the Bezoff space, so the whole logarithm of phi prime is in the Bezoff space. And by post-composition with smooth functions, we can exponentiate that. And this is a result by Petre. And then this is kept. This smoothness is kept under C infinity post-composition. Okay. In turn, this implies that the function is of 1 more degree of smoothness. Of course, if the derivative is here, then the function has 1 more degree of smoothness. This is essentially natural to understand, to believe. Okay. So finally, we use the boundedness of the Herglotz extension. So if the boundary values of phi are in the Bezoff scale, then phi needs to be in the Sobolev scale, because the Herglotz extension maps the trace to the original function space. Okay, so that's all. We only need to prove that. And what is the relation between gamma and the boundary parameterization of the domain? This is what I will explain next. Linking the boundary parameterization and the Riemann mapping. How can we do that? Okay, now is the moment to define what is a Bezoff domain. A Bezoff domain is as follows. We say that omega is a Bezoff sigma pp domain if there is a parameterization, that is a mapping from the unit circle to the boundary of the domain, such that it's bi-Lipschitz and is in the Bezoff class. Okay? Then we say that it is a Bezoff domain. Okay, it's just like a C alpha domain, the same. If it's, of course, simply connected. If it's multiply connected, then you can generalize easily this definition. Okay, now let's find the Riemann mapping of omega. Let's consider the Riemann mapping of omega, and let's take a look at what phi prime at the boundary. So let's assume, and now I am being, of course, bold, but let's assume that phi prime extends to the boundary. What would be phi prime in the boundary? Phi prime would be the evolution of phi at some point minus phi at the original point divided by the subtraction. This is clear, no? Because the function is holomorphic. Okay, good. Now, what is the argument of phi prime? The argument is the subtraction of the arguments. This argument minus this argument minus this argument, and this argument is the product. If you take this as a common factor, this can go as a common factor. This will be the argument plus the argument. No. So, and what are these guys? Let's see. This thing here in the boundary is gamma, by definition. This thing here, the argument of e power it is minus t. Well, with the minus, yeah. And what is this thing here? This is number 1. This is e power a minus epsilon. The difference is a vertical vector. So the argument is p halves. Okay, good. And then what is this thing here? What is this thing here? This is the phi at somebody that is slightly here. So this is somebody here. When this is approaching, this is the tangent. The tangent direction, no? So this is the same as the tangent direction, the tangent direction here, which is the argument of omega prime. Okay, so it's omega prime evaluated at this point here that is going here, and going back. Okay, so this is quite natural. So gamma can be recovered from omega and this is the information that we have. So the information that we have is the domain is Bezoff. So we have information on the regularity of this guy here. And we want to get information about this guy here, gamma, okay? But note that here in between we have something that is, that may create doubts, because this is phi, and we want to get the regularity of phi. So here we need to perform an induction argument so that we can bootstrap and get the final regularity for gamma, okay? So that's what we will do. Our information is the argument of omega prime is Bezoff. Now we assume that the claim is true for just any value that is smaller than s, and we will assume that s prime is greater than s minus 1. It's enough for our purposes, because then we will need to get some information back. and assume that S prime P is greater than 2. And there is always such a S prime for every S that we consider. We can always find an S prime that satisfies these properties. Okay. Now, first case, the basic case, if S is between 2 over P and 1, in fact, 1 plus 1 over P, it's still valid. And we assume by assumption, our statement is that phi is bi-Lipschitz, that omega is bi-Lipschitz. This is by assumption, so this is bi-Lipschitz. And if this is bi-Lipschitz, since we don't need to take any derivative because now we are assuming that S minus 1 over P, okay, S minus 1 over P is smaller than 1. So here, if you remember the definition of the Triebel-Lizorkin norm, okay, now I realize I haven't defined Bezov. Oh my God, I haven't told you what is Bezov. Bezov, sigma P is Triebel-Lizorkin sigma P. Do you like this definition? Okay, yes, I know. The tradition tells us that we have to use Bezov, but it's the same as Triebel-Lizorkin in the diagonal when P equals Q. Okay, these are the same spaces. So, okay, sorry. So here the definition is this first order definition that I was giving you before, and you don't need to take any extra derivative because this smoothness parameter is below 1. Okay, so this acts as a change of variables, and it's very easy to check that this keeps the Bezov norm. Okay, this preserves the Bezov norm. Okay. Now let's assume by induction, let's assume that S is greater than 1, and take S prime that is in this range, and satisfying that S prime times P is greater than 2. And by induction, we assume that this is satisfied for S prime. No, so phi is already in this space. Now W is also in this space. Okay, because S prime is smaller than S, and W is in S plus 1 minus 1 over P. So both functions W and phi are admissible Bezov parameterizations of the boundary. Lipschitz, they are both Bezov. So the composition, as I showed you before, is also in the Bezov scale. Well, there are some details here because these are okay. The function here is taking omega minus 1 is defined in R2, so you go into R. So it's okay. There are some details here, but you can check that this is satisfied. And also, clearly, this composition is also bi-Lipschitz. So here we can apply the result that I told you in the first section, that the composition with bi-Lipschitz Bezov mappings preserves the Bezov norm. Okay, this is what I told you in the first section. So we are done. We have seen that gamma, which is somebody plus this guy here, is Bezov, and this implies that phi is Sobolev, and that's all about the Riemann mapping. So let's go for quasiconformal mappings. Let's see what are quasiconformal mappings in the complex plane. Okay, what is a conformal mapping? Conformal mapping is a mapping sending circles infinitesimally to circles. Okay, as you can see with the Sagrada Familia, and they satisfy the Cauchy-Riemann equation that can be written as delta F equals 0. Okay, what are quasiconformal mappings? Quasiconformal mappings have the distortion bounded, the angle distortion bounded. So the idea is that infinitesimal circles are mapped to infinitesimal ellipses. Okay, and the exact way to control this will be this equation here. Delta bar F is smaller or equal than kappa times delta of F in absolute value. Okay, and we also ask that it's Sobolev homomorphism. Okay, the Beurling transform. What is the Beurling transform? It's the Beurling transform is the convolution of F with 1 over Z squared. Okay, but this, since the kernel is singular, this cannot be integrated. You need to take a principal value. So you need to take a limit here. Okay. Now this Beurling transform is essential to quasiconformal mappings because it has the following property. It maps for every Sobolev function. It maps the delta bar to delta. So okay. For us, let's see what is our quasiconformal mappings. Assume that F is a function from C to C, the complex plane. homeomorphic, assume that its distortion delta bar f divided by delta f is an L-infinity function with compact support. Okay, this means that f is holomorphic from at infinity, close to infinity. Okay, and the distortion must be bounded by 1. It's an infinite term. Okay, this is essentially that is quasi-conformal. And we don't ask that f is Sobolev 1 to log. We ask a little bit more. We ask that it's the so-called principal solution. That means that at infinity, this behaves like z. No, f minus z is a Sobolev function. So at infinity, this is essentially like z. Okay. Then this equation, this is called the Beltrami equation. Yeah, this is the equation that is satisfied by f, of course, because of this. Implies the following: mu can be recovered as the identity minus mu times the Beurling transform of delta bar f. This is just using this thing here and this thing here, combining these two facts with the fact that f minus z is Sobolev. Remember that you need this Sobolev thing in order to apply. You combine the three things, exercise, you reach this identity. And in particular, what this is saying is that to get, if you have knowledge about mu, the Beltrami coefficient, you can recover information about delta bar if you know where this operator is invertible. Okay? So we need to study the invertibility of this identity minus mu times the Beurling transform. And it's well known that Beurling is bounded in LP, it's bounded in Sobolev. And in fact, in Bessel potential spaces, in Triebel-Lizorkin scale, it's bounded. So it works well in the whole complex plane. Okay, results in the whole complex plane without boundaries, let's say, without boundaries. Okay, take a function, as I said, the principal solution to the Beltrami equation. And now we write here in our beautiful diagram, we put these these two elements, which are kappa divided by kappa plus 1 and 1 divided by kappa plus 1. These two elements are quite important because they are the critical exponents for our quasi-conformal mapping. Okay, why? Because as Astala showed in 92, delta bar f is in LP in all this region here. Okay, and in fact, Astala, Ivanets, and Saxman showed that the operator identity minus mu Beurling is invertible in all this range. This is called the critical range. Okay, open, no, not in the endpoints. Okay, good. This means that if delta bar f is here, then f is here. So the quasi-conformal mapping, you know, by assumption, we said that it was Sobolev 1, 2. It's here. But now we get some extra integrability. We get that it is here, Sobolev 1, p. Not in the endpoint, but for every p smaller than p sub k. Okay? Yes, it has all this integrability, at least locally. Okay? Okay. What if mu has some extra regularity? If mu is in VMO, vanishing mean oscillation, then delta bar f is in all L. So just having a slightly more than L infinity, just having VMO, we jump from here to the original, but not reaching L infinity. Just for every LP, not reaching L infinity. Oh, here you are. Okay. Okay. And of course the function f, the quasi-conformal mapping, will be locally in all the Sobolev space, Sobolev 1p. Okay, if mu is in the Helder has a certain Helder regularity, then the delta bar has exactly the same regularity. There is no loss now, and function f will have 1 degree more of regularity, of course. If mu is in Triebel-Lizorkin or in Bezov, this is why design means either B or F, okay, or either Bezov or Triebel-Lizorkin scale, then delta bar is in the same space, and the function f gains one more degree of smoothness. Okay, if mu is in Sobolev 1, 2, this was Cruz-Mateurovich. So if it's in Sobolev 1, 2, then the delta bar is Sobolev 1, 2 minus epsilon. So you lose the endpoint again. Okay. Exactly, and this was Klomp, Faraco, Mateurovich, and Zong that showed this. And of course, f is 1 degree more of smoothness. And if mu is Sobolev 1p, and p is smaller than 2, then there is a loss a loss of integrability for the gradient as well as for delta bar f. Sorry, the same loss, the degree of loss is the same that you had originally. So it's the critical interval. Okay, this is the loss that you have 1 over pk. Okay, for more results to cover the whole supercritical range, you can see Klopfer, Ruiz, Prats. This is me in in communications of pure and applied analysis. Bison, Klopp, and Norovich, and Bison and Cruz have some results in the whole critical and subcritical range. Okay, so what else about these? I think, but what is the moral? If mu is subcritical, there is loss. If mu is critical, you lose the endpoint. If mu is supercritical, we keep the regularity. Okay, this if there are no boundaries. So functions that are regular, mu is regular in the whole complex plane. It's compactly supported, but regular in the whole complex plane. Okay, and this is what we have. So let's move for quasiconformal mappings on domains. Now, what happens here? Consider again the same Riemann mapping as before. So we have the unit disk, you have the von Koch snowflake, and phi is the Riemann mapping. Now, since phi is conformal, delta bar of phi is 0. Okay, the Beltrami coefficient is 0. Of course, for conformal mappings, Beltrami coefficient is 0, and this means that it is in every Sobolev space. Okay, for every S and P. However, phi prime, as we said before, does not extend to delta bar to the boundary of the disk. So phi is not C1, and in particular, as a consequence, the derivative is not in any supercritical Sobolev space, because otherwise it would be C1 by the Sobolev embedding. So what is the moral? Why I'm saying this trivial thing? I'm saying this because the moral is that in order to study the regularity of the mu quasiconformal mapping between domains, we need to take into account both the regularity of the boundary and the regularity of mu. The two elements are important now. So in the Riemann mapping, it was enough the regularity of the boundary, and for quasiconformal mappings, we still need to take this into account. Okay, it's crucial. So now our result of this is in the same work with Curry and Arrow. Again, in the supercritical range, p between 1 and infinity, simply connected bounded domains. G is mapping omega 1 to omega 2. It's a mu quasiconformal. Now, if both domains are Bezoff domains and the Beltrami coefficient is Sobolev, then the mu quasiconformal mapping is Sobolev S plus 1. Okay, and it's bi-Lipschitz, moreover. Okay. Okay, if omega 1 is the unit disk, then the statement is if and only if. So this is sharp result. Okay, this is a sharp result. So if omega 1 is the unit disk and omega 2 is a Bezoff domain, then omega 2 is a Bezoff domain, and mu is sorry, Vera. Exactly. It's a Bezoff domain, and mu is a Sobolev mapping. If and only if G is Sobolev. Okay, so this will be if and only if. Okay. Now I'm saying this well. Yeah. If omega 1 is a unit disk or just a very regular domain. For simply connected domains, we can replace simply connected, sorry, for finitely connected. Okay. And for numbers that are not natural, for the smoothness, we can use this Triebel-Lizorkin. Here the restriction is what I told you in the first section. We need to, since we talk about first order differences, we are to show these composite rules. We don't have a proof for natural values of this unless we are exactly in the Sobolev space. Okay, so other q different than 2 and s equal to, we have no result for this. This is what I'm saying. Okay. Okay, what is the idea of the proof? So consider the following. We want to see, now I will talk first about just a self-map of omega. So take G that maps omega to me a quasi-conformal mapping with coefficient mu, that is Sobolev, SP in omega. And assume that the boundary is regular enough. What can we say about the regularity of its derivative? Okay, let's extend mu to the whole complex plane, okay, which is possible because the domain is Lipschitz. Now, by Sobolev factorization, we can express G as H composed with F, okay? And of course, this will be, F is a mu principal mapping, okay, the mu principal mapping. So it's a homeomorphism, and in particular, the image of omega will be omega hat, a simply corrected domain, and then H will be conformal. Okay, this is law of factorization. It's a classical result in quasi-conformal mappings. Now we can find then Riemann mappings for both domains, because the domains are simply corrected. Okay, and now let's talk about what happens. How can we find the regularity of G? Let's go step by step. First, F. F is a quasi-conformal mapping of the whole complex plane. Its coefficient, its Beltrami coefficient mu, which is just an extension. Maybe we can write it like this. Is an extension of mu to the whole complex plane. So let's say this restricted to omega would be equal mu, but mu is regular in the whole complex plane, not only in omega. Okay, and an infinity norm smaller than 1. You can create that. Now this function f will be bi-Lipschitz, of course, because it's the whole complex plane, and it's also quasi-conformal. Okay, of the whole complex plane, as I was saying. Yeah, this is the result that I told you in the previous slide. No, we can conclude this. Okay, this is a Klopp-Mateurovich, no, Cruz-Mateurovich. Okay. Second, phi 1 is mapping is a Riemann mapping. This is the second section of this talk. This Riemann mapping needs to be Sobolev, but we have shown it again already. Okay, and it is bi-Lipschitz. So both mappings are bi-Lipschitz. Okay, both mappings are bi-Lipschitz, and both mappings are Sobolev. So the composition, as I showed you in the beginning, is also Sobolev. This means that the boundary, the trace of this composition is in the trace space that is Bezov. So the domain omega hat has the same regularity omega. Good. Omega is a Bezov domain. This is crucial, because now phi 2 also will have the same regularity. Okay, it will be Sobolev by the Riemann mapping, because it's a Riemann mapping of omega, and omega is regular. And also omega hat is regular, sorry. And omega is regular also, so H composed with phi 2, which is also a Riemann mapping, is Sobolev as well. Good. Then everybody is Sobolev. We compose everybody is Sobolev. Everybody is bi-Lipschitz. We compose everybody, and we get a Sobolev function. And that's all. Quite simple. So essentially, this is a consequence of the Riemann mapping result. Okay. This kind of scheme was already shown by David Kalai for the case written like this, for the case of the Holder scale. I didn't mention in the slides. Okay, and finally, okay, I will stop here. I won't talk about this last part. I think then I will give you time for maybe short questions or so. Okay, so that's all.
Okay, thank you very much, Martí. Any questions or remarks?
Okay.
If not, we can thank Martí. Okay, the next talk will be in 2 weeks, and the next speaker is Alejandro Mas. So, have a nice day. See you. Thank you very much, Martí, for the interesting talk.
Gracias, Martí, por la charla.